for the invitation. Nice to be here. I'm going to talk about mainly this first paper from August, and then a couple slides on this more recent one. And the subject is Ringdown at finite coupling. So here's a quick outline. Let's start with the motivation. So we're interested in thermal correlators, and in particular, this is the thermal 2-point function. So here O is some Hermitian operator. It can be a local operator, or it can be in momentum space, and beta is the inverse temperature. So we're interested in systems with infinite entropy. For such systems, there are no recurrences at late times, and so we expect that C of t thermalizes, which means that it goes to zero, assuming that the 1-point function of O is zero. Okay. So the kinds of systems I have in mind are, you could have a spin system at infinite volume, in which case there's infinite entropy because the system size is infinite, or you could have a large n gauge theory, in which case there are an infinite number of local degrees of freedom. So in either case, we expect thermalization, and it should vanish at late times. And the question is, functionally, how does that happen? So it's not very descriptive to say it vanishes. We want to know functionally how it goes to zero, and it could be in general, we don't know. It could be a power law or an exponential or something more complicated. But in some sense, the simplest possibility is what I've written here, where it's a sum over exponentials. Now we want this to go to zero, so the imaginary part of these frequencies omega n has to be negative, and dn are just some complex coefficients. So I'm going to call this ring-down behavior, because what it looks like is the ring-down phase of black hole mergers. So when two black holes merge, the signal at very late times is dominated by the quasi-number mode of the final black hole, and you find a signal that looks like this with these exponentials. So the dn's are just some complex coefficients, and the omega n's are some frequencies. So this is not, I haven't derived this form, and generically it's certainly not true, but this is the simplest possibility, and we want to understand this possibility first. So it's useful now to Fourier transform this function, and now we get the spectral density, which is C of omega, and these complex frequencies omega n are just poles of C of omega. Now we can start looking for examples of this behavior, and the surprise is that almost all examples that are known explicitly are large n gauge theories at strong coupling. So in this case, we know the answer because of ADCFT, and in fact, this analogy to ring down of black holes is made precise here because, of course, holographically, the thermal state is dual to a black hole in ADS. And these poles of C of omega are the quasi-normal modes of this ADS black hole at infinite lambda. So this is sometimes called the Christmas tree of quasi-normal modes. And it's more or less generic. I mean, in the angle of these lines depends on what dimension you're in. But it's always there as long as you're in an ADS black hole, and there can be more poles inside, but asymptotically it just looks like these straight lines with evenly spaced poles. Okay. So that was at strong coupling, and the other limit that we can do explicitly is zero coupling. So in free field theory, we can do the computation explicitly, and we find a very different answer. So here we find, instead of poles, we find branch cuts. And the real part of these cuts extends from minus k to plus k, where k is the spatial momentum of the operator. So here, this is the 2-point function of glue balls in n equals 4 at 0 coupling, and k is the spatial momentum that labels the operator, and we find these branch cuts. Yeah, so these two pictures look really different. And it's not clear what happens in between. There has to be some transition between the two, but at finite lambda, we don't know if there's poles or cuts or both. You can try to do various can try to motivate various perturbation schemes, like you can start at 0 coupling and then try to reach some perturbation theory. It doesn't work particularly well. There are various papers on this, but there's no fully consistent story of that resummation. And similarly, you could try to start from strong coupling and come up with some toy holographic model, and but we don't really know in what sense that's controlled. So at finite lambda, it's an open question what the complex frequency plane looks like. So this is not even a question of numerics or quantitative the locations of poles. This is a question of the analytic structure, a very basic question that we do not know the answer to. So that's the question we want to try to address. And another way to ask this question is, so at finite lambda, we have a black hole, but the ADS scale is of order of the string scale. So this is a very non-local setup. And so you can say we have a stringy black hole. So this is in some sense, the definition of a stringy black hole. And the question would be, what does a stringy black hole look like when you hit it with a perturbation? How does it ring down? So we can try to answer that question, but it's not very smart to try to ask how the metric looks like, because that's might not even be a well-defined question. So instead, we asked a question that's less obvious from the bulk perspective, but at least it's well-defined, which is what is the location of these poles in the complex plane? And then we can try to extract some kind of information about the bulk geometry from the locations of these poles. So finding the poles is a well-defined numerical question, and then inferring geometric properties is less well-defined, but it might be the only possible strategy. So that's the philosophy I want to take today. Any questions about this motivation? All right. So in order for this philosophy to make sense, I have to show you that, in fact, these quasi-normal modes, these poles in the complex frequency plane, can indeed tell us something about geometry. And so that's what I'm going to review now. So at infinite coupling, we just have holography. And to compute these poles, we need to solve a classical wave equation on the black hole background. So here's the black hole. We're going to leave the function f of r more or less generic, but this is a rotationally symmetric and static solution. And in this background, the wave equation takes the form written here, which is the one-dimensional Schrodinger equation in a potential v of r. And here, the tortoise coordinate z is defined by dz equals dr over f of r. And so now all we need to do is to solve this one-dimensional Schrodinger equation. And to get various Green's functions, we have to compute various things. So for instance, if we wanted to compute the retarded Green's function, we would look for the solution that's ingoing at the horizon, which is z equals infinity. And then we would read off the behavior at the ADS boundary, which is d = 0. So at the boundary, there's two possibilities. There's a non-normalizable source here, which is A, and then there's a normalizable response, which is B. And the retarded Green's function is the ratio, B over A. Now, when the source vanishes, when A = 0, we have a mode that is both normalizable and ingoing at the horizon, and that's called a quasi-normal mode. And so what this implies is that the quasi-normal modes are indeed poles of the retarded Green's function. Okay, so let's do a few examples. So we can start with CFT at infinite volume. And now the redshift factor f of r is r squared minus 1 over r squared. And the potential in this case is monotonic. So at the singularity, r = 0, it goes to minus infinity. At the horizon, it goes to 0. And at infinity, it goes to plus infinity. Okay. And the quasi-normal modes are shown on the right. So these are just obtained by solving the wave equation in this potential. They're not exactly straight lines, but they're almost straight lines, and you can compute them numerically on a computer. So now we want to try to extract something about the black hole geometry from this spectrum. And to do this, note that we have two asymptotic limits that you can take. You can go to omega equals plus or minus infinity, or you can go to omega equals minus I infinity. So here we have these lines of poles, and they're separating the complex plane into two asymptotic regions. And you should think of these lines of poles as anti-Stokes lines across which the asymptotic behavior changes. Now, omega goes to plus or minus infinity is very natural. This is the usual high energy limit. And this is something you can take all the time, no matter what correlator you have, no matter if it's holographic or not, you can always go to high energies. A limit that you cannot always take is omega goes to minus I infinity, because that relies on the correlator being meromorphic along this direction, which is not always true. In this case, it is true, so we can try to take this limit. Now let's think about omega goes to minus I infinity. So imagine we're doing the WQB approximation, which is valid at high energies. In WQB, what you're supposed to do is to look for turning points of the wave equation, and these are given by V equals omega squared. So here we have this monotonic potential, and we see that there's two ways to probe high energies. You could go to r equals infinity, in which case the potential goes to plus infinity. And so this is probing omega equals plus infinity. So this is the ordinary high energy limit. And what we've learned is that high energies is just probing the boundary of ADS. This is the OPE limit. So this is kind of boring. But the other thing you can do is go to r equals 0. And then the potential goes to minus infinity. And so the frequency omega has to go to minus I infinity. And so what this says is that omega equals minus I infinity is probing the black hole singularity. So here I've drawn some geodesics, and you see that geodesic 2 is bouncing off the black hole singularity and hitting the other side. And this is called the bounce geodesic, and it's the contribution to the correlator in this limit, omega equals minus I infinity. So one thing to remember for later is that in this limit, the correlator exponentially decays with some decay rate c as omega goes to minus I infinity. And you might think that if we want to understand what happens to the black hole singularity at finite lambda, you would try to understand how this exponential decay is modified at finite coupling. So that's one question that we're going to ask today. So we can keep going with more examples. So here's it's a slightly more complicated example, which is a charged black brane. And now what happens is that the potential is no longer monotonic, and it goes to plus infinity at the black hole singularity. So the modes now look like this, and you see that there's this new line of imaginary poles. So the interpretation is that we now have this stable minimum of the potential, and these imaginary modes are just virtual bound states that are localized at this minimum of the potential in between the inner and the outer horizon. Okay, so this new line of poles have this geometric interpretation that probes behind the outer horizon. And so now you could ask how to probe the black hole singularity, because you can't actually go to minus I infinity on the imaginary axis, but you can still go in these complex directions off the imaginary axis, and you can show that indeed that probes the singularity, which is now time-like. So here's the last example, which is the most rich, which is a quantum field theory at finite volume. So now the difference in the redshift factor is that there's this +1 here in the middle. And we can now take the large spin limit. So by spin, I mean the spin of the perturbation. And now the potential develops an unstable maximum here, and that's called the photon sphere. And it has a metastable minimum and an unstable maximum, and the quasi-normal modes look like this. So now you have these modes that are very close to the real axis, and all those are modes that are localized at this metastable minimum near the boundary. So these are orbits around the black hole that are taking a long time to tunnel in, because they have to tunnel over this potential barrier. And so we expect the imaginary parts of these modes to be exponentially small in spin, and that's indeed what you found. So you might ask, how do we actually probe this unstable maximum, this photon sphere? And to do that, you can take the spin to I infinity. So you can analytically continue in the spin. And then you find these iconal modes. So here, capital omega is the velocity of null geodesics at the photon sphere. And gamma is called the Lyapunov exponent. It's related to the derivative of the potential at the maximum. So this was just a few examples that was meant to clarify that if you have the spectrum of modes, you can learn basically everything about you can learn many interesting things about the geometry, like all the interesting features we've seen you can extract from the modes, even features of the geometry behind their horizon. So this is very encouraging, because it means that we don't have to think about the geometry anymore. We can just think about the poles, and these are much more well defined from the perspective of the boundary CFT. So now we can just forget about the geometry and think about the poles. Any questions? Yeah. Oh. Mhm. Mhm. Yeah, I think so. On the other hand, certainly you can have situations in which there's a non-vanishing one-point function, but there's no black hole. But yeah, I think if you have the quasi-normal modes, you should be able, all that information should be also be in the one-point functions and the OPE coefficients. It might be very obscured, because the one-point functions are essentially short-time data, and the quasi-normal modes are long-time data. So they should be equivalent, but it might be very hard to understand how they're related. Anyone else? Okay, so now we can move away from the bulk and try to understand the boundary. So I'm going to make a few assumptions which simplify the story a lot. So the first assumption is that we have infinite temperature. So in a continuum theory, this would not be well defined. But in ordinary quantum mechanics, you can certainly do this, and in this case, the correlator is well defined. So in this case, C of t is just a trace of O of t of O of 0. So this is going to simplify things because the temperature has a scale, and we want to get rid of everything that has a scale besides the coupling. So that's the first assumption. Next, we want to assume that the theory is just quantum mechanics. And so it's not field theory, it's just quantum mechanics. And so this correlation function is non-singular at t equals 0. Ordinarily, there would be a coincident singularity, but not in quantum mechanics. And finally, we're going to assume a single dimensional coupling J, and then the units of J should be energy. Okay, so that's the only scale in the problem. So now we can, assuming these three things, we can write down what's called the moment expansion. And this is just the Taylor expansion of C of t at the origin, t equals 0. If you had a temperature, you could still do this, but you would want to Taylor expand the two-sided correlator, so there would be no coincident singularity. But in our case, we have infinite temperature, and we just Taylor expand around the origin, and these mu n's are called the moments of this correlator. So here. So first of all, I use the fact that C of t is even. That follows from cyclicity of this trace. Second of all, I use the non-singularity of C of t. Okay. And so now we can use dimensional analysis to say that these mu's have to scale like j to the 2n to make up the dimensions. And so all we're doing is perturbation theory. So if we truncate this sum at order n, then we're doing perturbation theory up to order j to the 2n. So this moment expansion is just the perturbative expansion. And it turns out that it has a finite radius of convergence, which we can call beta naught over 2. And up to this scale, this perturbation theory actually converges. So this is not like the usual situation where perturbation theory is asymptotic. Under these conditions, perturbation theory actually converges, and this is going to be very important for us. So by dimensional analysis, beta naught has to scale like 1 over j. And in fact, we know more. There's a conjecture that's been checked in many examples, which is called the universal operator growth hypothesis. And this says that in any chaotic theory, these mu2n's has to take a universal form at large n. Okay, and that's this form written here. And again, beta naught is just a scale, which is setting the radius of convergence of this sum. Okay. And so suppose we've done this moment expansion, and we've computed to a given order, and now we want to compute the quasi-normal modes. So what that means is that we want to fit this moment expansion to an infinite sum over exponentials with some coefficients dn. Now, suppose that we're able to actually solve this problem, this fitting problem. If we look at the left-hand side, it has a finite radius of convergence. But if we look at the right-hand side, it actually converges for all times t greater than 0. So if we were able to solve this problem, then we've extended the perturbative expansion to all times t greater than 0. And by dimensional analysis, omega n is scales like j, and so there's a j in the exponential, and so what that means is that we're doing a non-perturbative resummation of this correlator. Now that would be bad if we had to actually resum Feynman diagrams, because that's always hard. We're not going to do that. Instead, we're just going to fit to exponentials, and that exponential fitting procedure is going to do the resummation for us. Okay, so then the problem is just suppose we have a function and we only know it over a finite range. How do you fit to exponentials? It turns out you can solve this problem using linear algebra, and I'll explain that now. So the first thing you do is you truncate to a finite number of exponentials, s, and then you solve the fitting equations on a grid of size 2s. So here in this picture at the bottom, I show that grid, and here we know that the correlator up to time beta naught over 2, and then we have a grid of equally spaced times over which we're going to fit this, over which we're going to solve these equations. Now we have 2s equations and 2s unknowns, which are the dn's and the omega n's. So that's enough equations for the number of unknowns. And in this setup, s is finite, but at the end, we have to take s goes to infinity, and we hope that the answer converges. We made an important assumption, which is that the answer is actually a sum over exponentials. That's not in general true. And if it's not true, the procedure will let us know, because it will not converge. If it does converge, then we know our assumption was correct, and we'll find an answer which makes sense in the limit s goes to infinity. So it's important here that the range over which we know the function is not, it does not look like an exponential. It has not decayed very much. So the statement is that even if the function hasn't decayed very much, if you know it extremely well, you can still do this fitting procedure and extract these exponentials in this limit. So how do you fit to exponentials? So let's introduce a little bit of notation. So I'm going to have a Hilbert space of operators O, and the inner product on this Hilbert space is just the trace inner product. So trace O prime. And then the strategy is to look for an operator U tilde, which satisfies this equation. The jth power of U tilde acting on O, overlap with O, is equal to the correlator at time j times delta t. So here delta t is just the spacing between the points on the grid. So here U tilde is, we can think of it as some kind of modified time evolution operator, because you know it's acting as time evolution on this initial state overlap, and you get the correlator. But it's important that it's not equal to the actual time evolution operator, as we'll explain now. So let's assume that we're able to solve this this equation. Then we could compare the left-hand side and the right-hand side here. And we see that one way to solve this equation is if the eigenvalues of U tilde are precisely these e to the minus I omega n delta t's. Okay? So importantly, omega n is not real. And so the eigenvalues of U tilde are not on the unit circle. So this means that U tilde is actually non-unitary. And so that's why I call it a modified time evolution operator, because it's a version of the time evolution operator which is non-unitary. Okay. So given this eigenvalue equation, we can now solve it by making a non-SATS where the eigenvalues where the eigenvectors are a linear combination of U tilde to the j acting on O. And then we plug in and we get an eigenvalue equation, which we can now put on a computer and solve. So here, these matrices Mi that appear in this equation just depend on the correlator on the grid, but we know that, and so everything in this equation is known, and we can now solve for the eigenvalues on a computer. Okay. So I just want to illustrate this procedure in two examples after I go get a drink of water. I'll be back in a second. So here's two examples. So in the first example, the correlator is 1 over cosh of pi t over 2. And this, of course, has quasi-normal mode behavior at late times. At late times, it's a sum over exponentials, and the exponentials are discrete. And the function is plotted here. And what I've done is I've taken the Taylor expansion of C of t around the origin and then truncated at some finite order. And then fitted that that Taylor series to a sum of exponentials. So the Taylor series converges up to t equals 1, and so that's why you see it blowing up at t equals 1. And the exponentials you find are on the right. And this is the correct answer. So we have discrete poles on the imaginary axis, which are the quasi-normal mode frequencies of this correlator. Okay. So that was an example that had quasi-normal mode behavior. In the second example, we have power law decay. So this is not a sum of exponentials at late times. But if you look at it over the range of convergence, the two functions look very much the same, and I don't think you would have been able to tell that one is exponentially decaying and one is power law decaying. But this procedure can tell. So if you run this procedure for this function C of t, which is power law decaying, then you find an answer that's on the right-hand side. So here, as you increase the grid size, the poles start to accumulate, and you do not find a conversion answer. So this is a branch cut on the imaginary axis, which is indicative of power law decay at late times.
Sorry, in the first plot, do you have like many points, but they pile on top of each other, or is it just 3 points?
In the first plot, it's just 3 points, but of course, if you keep going, there will be more. Yeah.
But it's a bit counterintuitive because you truncated the Taylor series, so it's not exactly the set, is it?
Right. So it's not exactly the set, but the statement is at least the first few poles have converged. If you were to go far down in the complex plane for a fixed grid size S, you would not find the correct poles. But as you take S goes to infinity, it will converge.
Thanks.
Sure. Yeah, so this is probably like S equals 100 or something. So, you know, far close to the real axis, it's converged very well. Okay. So let's take stock of where we are. So we started with a function C of t, and we fit it to sum of exponentials by constructing this modified time evolution operator U tilde, whose eigenvalues are the omega n's. Now the omega n's are complex, and so this is a non-unitary version of the time evolution operator. When we have dissipation that emerges from unitary dynamics, we say that the arrow of time has emerged, and in this case, it's clear that that's what's happened. So we started with this very strong assumption that we have a discrete set of poles. If our assumption is valid, then we'll find the right answer, and we'll find convergence in the limit S goes to infinity. If it's not valid, then we'll find accumulation of poles into cuts, or maybe even worse than cuts. So in classical chaos, there's a very close analog of U tilde. In this case, you have the time evolution operator, and you coarse grain it to find a non-unitary version of the time evolution operator. And the eigenvalues of this operator are called the Ruel resonances. And if the system is very chaotic, then these are discrete. In the case of holographic theories, there should be some bulk interpretation of U tilde, and it should be an operator whose eigenvalues are the quasi-normal modes. And this was constructed by Ba, Chen, Maldacena in this double cone geometry. And the way the non-unitarity works is that you have to impose an I epsilon prescription at the black hole horizon because there's a singularity there. And that I epsilon prescription gives you a non-unitary operator. Okay? Questions about this procedure? Okay. So
Maybe
now,
I have another one. So in field theories, we have the singularity.
Mhm.
So how does that enter into the game?
Yeah, so in the field theory, the natural thing to do is to put the two operators on the opposite sides of the thermal circle, and then do a Taylor expansion. And so that's something that's well defined, and you can again define these moments. In that case, they again satisfy these universal asymptotics. And actually, even in SYK, we have some unpublished work where we do that. But yeah, in a CFT, in principle, you can define this moment expansion. These are not directly related to the OPE coefficients because the two operators are on opposite sides, but you can express them in terms of an infinite sum over OPE coefficients.
I see. Thanks.
Sure. More questions? Okay, so now we have to do an example. And for an example, we choose the SYK model. So this is a model of fermions that are interacting via this Q pairwise interaction. And here n is the number of fermions, and it's taken to be strictly infinite. The couplings are averaged, disorder averaged, with strength capital J, and they scale in a particular way with n as n goes to infinity. So we need strictly infinite n so that the correlator decays to 0 at late times, because the entropy is finite at finite n. And the reason to study this model is that it's very simple, and you can do computations extremely accurately. At infinite n, we have an integral equation for the 2-point function called the Dyson equation, and it's written here for q equals 4. And this equation can be put on a computer. And at infinite temperature, you can compute the perturbation theory in J and compute these moments, and you can compute the nth moment in polynomial time in J. So this is very important because for some generic spin system, it takes exponentially long in n to compute the moments, and so the record number of moments you can do is I think the best they've done is like 45, and so that's pretty good. But here we want to ask very subtle questions about the complex plane, and you need to know the function extremely well. And so it's very important that we have a polynomial time algorithm here. So if you run this for a while, you can get 2,000 moments in 2 months, and this is a precision of 10 to the minus 1200 for the function. And so we know the function extremely well up to this finite range. Now it's important. All this precision is very important because if you're at a frequency that's of order like minus 10 times I, the contribution of that to the correlator goes like e to the minus 10 times t. So it's immediately killed exponentially. And so if you want to be able to compute these frequencies, you'd better know the correlator to like crazy precision. And so that's the reason to study SYK, because we have that kind of precision. And here's the answer, the ones that have converged so far. And let's explain each part of the plot. So the color of these points is denoting the phase of the residues, dn. So remember, dn are these complex coefficients that appear in front. The size of the points is the magnitude of dn, and it's on an exponential scale. And so the ones at the top, in fact, are dominating exponentially over the others. So all of the solid points here have converged. There are these hollow points which have not yet converged. And the pattern is that the ones that are closest to the real axis are converging the fastest, and actually on the edge of the tree, those ones also converge first, and then it kind of converges inwards. And so I expect that if you were to compute more of the resonances, you would find that this whole tree is filled out in the middle there. So we find a few surprising properties. The first being meromorphy. So what I mean by that is that the spectrum of poles is discrete and there's no cuts. Now, this is not something that you can actually prove numerically, but you just observe that there's no accumulation of poles. And in particular, up until here, so this is like the imaginary part is like 6, all of the poles that have converged to 4 digits, and there's no accumulation that's obvious. Now, it could be that you just run it for another year, and then there's cuts that appear. but I didn't see any sign of that showing up. So it looks like there's more poles, but no actual accumulation of poles. This the second property we see is this tree structure. So if we look at the edge of the spectrum, it's two straight lines, and they're at some angle from the real axis. And the final property is exponential decay. So we can look at the residues of these poles, and we find the exponential decay property that I was noting at the beginning of the talk. That was a signature of the singularity. Okay. So here we have S by K at infinite temperature, and it's not maximally chaotic. It's chaotic, but not maximally so, and it's really not a black hole at all. It's a very stringy black hole, but here we see that all these properties of ordinary black holes seem to survive in this stringy limit. So this is very surprising, and it seems to be telling us that there's some inherent geometry, even though we're not in the gravitational regime. So you might want to ask, for instance, what happens to the black hole singularity at finite coupling? And from what I said before, you might want to look at the properties of the spectrum at omega equals minus I infinity, and in particular, you would want to compute all these poles down here. You might think that there's some kind of random matrix theory that underlies this statistics of these poles. So if you look at open systems, at chaotic open systems, you find that the edge of the spectrum is very regular, but then the middle is characterized by some non-Hermitian form of random matrix theory. So that's one conjecture for the spectrum that you find. To check this conjecture, you would have to actually compute more poles. And this is a concrete question, a concrete target for computation. Okay, so we have this. We also have this parameter Q, which is the number of fermions in the interaction, and we can now vary that. And here's what happens. So as you increase Q from Q equals 6 to 20, the tree closes in, and by Q equals 20, they're already all imaginary. And we can actually come up with a crude bulk model for what's going on here. So at large Q, all the Q and M's are imaginary, and in fact, the theory is solvable at large Q, and you find that that's dual to ADS2, even away from low temperatures. The model at low temperatures is dual to ADS2, but at large Q, it's dual to ADS2 at any temperature, in the sense that the 2-point function looks like the 2-point function in ADS2. So here's the metric of ADS2, and the Q and M's are this first picture here. So they're all imaginary. So imagine that we want to try to come up with some toy model for the transition from large Q to Q equals 4. Well, we might want to add a perturbation to this redshift factor that blows up at the singularity. So here's a toy model for that. So we have these parameters L1 and L2, and at R equals 0, there's a singularity in f of R. And now what you can do is just compute the quasi-normal modes for this toy model metric. And what you find is that you increase L1 and L2, and generically, the poles open into this Christmas tree. And so this is roughly speaking, what's going on here. So we have imaginary poles at large Q. It opens up into this Christmas tree. And so this is a toy model for the stringy black hole, and it supports the idea that this Christmas tree is somehow related to the black hole singularity.
Sorry, this is only toy model, or you can match your result, numerical result for some L1, L2?
Yeah, so this is only a toy model, and this is very important because so one feature that you see here is that there's just not as many poles. So this is something you can prove. So in these holographic toy models, you can never have too many poles because you can show that there are no zeros. And if there are no zeros and you need exponential decay at large real frequency, you can show that the density of poles cannot be too high. In these setups, the density of poles is much larger, and in fact there are zeros. And so you can show that this no zero condition is violated at finite coupling.
Okay, thank you.
But the idea of getting this Christmas tree is something you can come up with a toy model for. Yeah, exactly. That's right. So in fact, that's basically the only difference. So you can have these toy models, and then the only thing you cannot reproduce is the bulk of this spectrum. So you might say, indeed, that a stringy black hole should have this edge of the spectrum that you could reproduce in holography, and then some bulk stringy behavior that you cannot reproduce in a black hole. Okay, and more questions? Okay, so now let me just give a quick outlook and we can conclude. So we saw this a surprising property that the correlator is meromorphic at finite coupling, and you might want to try to understand that better. So in classical systems, there's a whole story here, and it's actually understood what this meromorphy means. So this the theorem is as follows. So let's consider a classical dynamical system, and in this system, we should have periodic orbits, and they should all be unstable, and moreover, they should be dense in phase space. So this is called an Anosov system, and under these conditions, you can show that C of omega, the spectral function, is meromorphic, at least in a strip of the complex plane. So what this says is that these Anosov systems, and these Anosov systems, you should think of as globally chaotic in the sense that all of phase space has exponential divergence of trajectories. So these are the most chaotic type of models, and the theorem says that, well, you might have thought that chaotic systems are very complicated, but in fact they're very simple, at least structurally. So the 2-point function has this very simple structure where it has to be meromorphic in a strip of the complex plane. So the most complicated types of systems are not globally chaotic. They have some chaotic regions and some integrable regions of phase space, and they have a very complicated 2-point functions. But in Anosov systems, the 2-point function has a simple analytic structure. So that's the classical theorem, and now one wants to generalize this to quantum systems. It's not at all clear how to do that. In this paper, I tried to come up with another condition that's related to meromorphy, yeah. So in quantum systems, you have these Longshot's coefficients, which are related to operator growth, and you can show if they have a particular asymptotic form, then you can show that the 2-point function is meromorphic. So this is some kind of condition on operator growth that leads to meromorphy, but the connection to Anosov systems is not clear. You might have said that maybe all large N chaotic systems have a meromorphic 2-point function, but actually that is not true. So here's a simple counterexample. So let's take SYK and we deform by this Q equals 2 Hamiltonian. So the Q equals 2 Hamiltonian is just a free fermion, and so this is an RG flow from a chaotic theory at high energies to this free fermion integrable theory at low energies. And you can think of this as a quantum analog of a classical system that has a mixed phase space. So here we have a system with a Hilbert space that is chaotic at high energies and integrable at low energies. And in this case, you actually do not find a conversion spectrum of poles. You find this branch cut. So here we see that the poles are accumulating along this cut. So the upshot is that meromorphy is certainly not generic at large N, and one wants to understand the conditions to get meromorphy in the 2-point function. In particular, one thing you would want to prove is at N equals 4 at finite lambda is meromorphic. That would be my guess, but it's not clear how to prove it. So here's some other open problems. The first problem is we just need more examples. So if it's true that these eigenvalues are generic properties of chaotic systems at finite temperature, then we should find more examples where we can do the computation quantitatively. So for instance, a large N matrix quantum mechanics is the simplest. Well, in my opinion, it's the most approachable example. And then, of course, there's more realistic examples also, like 3D Ising or QCD.
Yes.
And we want to know what kinds of universal structures emerge. So is there always a Christmas tree? Is there always meromorphy, et cetera, et cetera? And another simple question you could ask is there are these higher dimensional SYKs, and you could ask if you could find these long-lived quasi-particles that correspond to stable orbits around the bulk stringy black hole. Okay, that's it. Thanks.